Okay, I'm going to work through example 1 on the non-constant acceleration motion in 2 dimensions. Worksheet. This is take 2, so I'm hoping it works okay this time. So we have relative to the origin, the position vector of a speedboat is modelled by r is equal to 2t plus 2I plus 12 minus t squared j, where I and j are unit vectors perpendicular and parallel to the beach. So we'll keep I positive x as usual, j unit vector positive y. I is perpendicular to the beach, so that means the beach is running like this, in this direction. Obviously it's a straight beach. So we want to calculate first of all the distance of the boat from the origin when t is equal to 2. So if I let t equal 2, then I can find the position vector of the boat from the origin. So 2 times 2 is 4 plus 2 is 6i. Let's see if that's 4 plus 2, so you can see what I'm doing. Plus 12 minus 2 squared j. Don't forget to underline your vectors. That gives us 6i plus 8j. If you want to work in column vectors, then please do. It's absolutely fine too. I'm going to do this one, i's and j's. The next example, I'll do column vectors. So you could write r as 2t plus 2, 12 minus t squared in columns. But I'm going to run out of room if I do that. So I'll keep this one as i's and j's. So if we've gone 6 cross 8 up, the distance from the origin is Pythagoras. So we're going from a vector quantity to a scalar quantity, and it's just straightforward, Pythagoras. So it's the magnitude of r. So that's square root of 100, which equals 10. There's no units in this question. I'm assuming it's meters, but we don't worry too much about units in maths. So the distance, so to get from position to distance, you find the magnitude of the position vector. Part 2, you may not see anything like this again, but sketching this graph, the position of the speedboat is dependent on t. So t is what's called a parameter, and it's going from 0 to 3. So we can find the position of the boat for some different values of t. So when t is 0, r comes out as being 2i plus 12j. When t is equal to 1, r is equal to 4i plus 11j. When t is equal to 2, we've got 6i plus 8j. And when t is equal to 3, r comes out as being 8i plus 3j. So we're actually plotting this with t as a parameter. So to sketch the path of the speedboat between t equals 0, t equals 3, we can just look at where it is for each value of t. So r is going, the I components are going 2, 4, 6, 8. So that's our horizontal component. The vertical component is starting at 3, going up to 12. So, 2, 4, 6, 8, 10, 12. Like so. And then if I plot each of those points, when t is 0, we're at 212. When t is 1, we're at 411. So it's going to be there. When t is 2, we're at 6, 8. and when t is 3, we're at 8, 3. And so you actually get a quadratic curve that's coming down like this. And it's a quadratic because we have this quadratic in the j component. So that's the path the speedboat is making. Sorry about the smudgy ink. It's a disadvantage of being left-handed. Right, part 3. Find expressions for the velocity and acceleration of the speedboat at time t. So the stuff we did on non-constant acceleration where you differentiate integration, you can do the same for vectors. So the velocity is when you differentiate the position with respect to time. Again, if you prefer these column vectors, that's fine. So I'm differentiating the I component, which gives me 2. And then I'm differentiating the j component, which gives me minus 2t. Like so. So that's the velocity. And then the acceleration is dA dt. If I differentiate 2, I get 0, and then differentiating the j, we get minus 2j. The other bit of part 3 just asks whether the boat is ever at rest. So if it was at rest, the velocity would equal 0. The velocity can't equal 0 because whatever time you're putting into the velocity, you're always going to get a velocity of 2 in the positive x direction, and so it can never be 0. So never at rest. As v cannot be 0. So you'd have to have 0i plus 0j as a possibility for it to be 0. So, words to that effect. So, it's never at rest, it's a velocity, cannot be 0, is always 2 meters per second in the I direction. Right, part 4. For t equals 3, calculate the speed of the boat. So, when t equals 3, the velocity, so I'm plugging into here, is equal to 2i minus 6j. And to get from velocity to speed, you need to find the magnitude of the velocity, which is the length of the vector. So that is the square root of 2 squared plus minus 6 squared, which is square root of 40. You might want to reduce your accuracy down a little bit, because it's a mechanics question. So that's the speed. And then you're also asked to find the angle that this makes to the line of the beach. So the line of the beach is this way, and the boat is travelling at 2i minus 6j. So it's travelling in this direction. And so we're looking for this angle here. So the angle with the line of the beach, we've got 6 down, 2 across, and so we can use tan theta is equal to 2 over 6. And so theta comes out as being 18.4 degrees. And then the last part, 5, suggests why this model for the motion of the speedboat is unrealistic for large t. So I think the easiest thing to do here is to go into velocity. So for large t, you're going to have an unbounded velocity. It's just going to be getting quicker and quicker and quicker and quicker, which isn't realistic. So as t gets larger, the velocity gets larger. which is unrealistic. For large T. So something along those lines. So that's example 1. I'm going to do example 2 on a separate clip. I hope that's all okay. If not, please get back to me and I'll explain it a bit more. Okay?